Good evening. My name is Chris Leclerc, and on behalf of the Kamloops Exploration Group, welcome to the third talk of the 2021 Kamloops Exploration Group Lecture Series. Over the next couple of months, KEG is excited to host and share the awesome 6 remaining virtual lectures that have been arranged. Before we get started, I would like to acknowledge that we are hosting today's talk within the unceded traditional lands of the Secwepemc Nation. As a not-for-profit organization, the Kamloops Exploration Group relies on sponsors to aid in hosting events such as this lecture series. Tonight, we would like to thank Examin Mining Corporation for being the sponsor of tonight and the remaining 2021 lecture series talks. Before we get started, I would like to inform you your microphones are muted and your video cameras are turned off. Throughout the talk, if you have any questions, we ask that you type it into the Q&A tab, and we will try to get to them at the end of the talk. Moving on to our speaker for this evening, I would like to introduce Roger Paulen. Roger Paulen is extremely experienced in surficial mapping, drift prospecting, and process glacial sedimentology. Apparently, he is also a whiskey aficionado and motorcycle enthusiast. Roger is currently a research scientist on the Geologic Survey of Canada GEM program. We are really excited to have Roger Paulen with us. A couple of days ago, I shared this talk advertisement on my personal Facebook account, and a good friend and mentor commented to say, quote, "I can guarantee you it will be good. Roger Paulen always gives killer talks." For those of you that would like to know more about Roger Paulen, you can find his biography posted on the KEG website. So, without further ado, please join me in welcoming Roger Paulen.
I can just imagine all the clapping now. So I'm just going to share my screen and jump right into this. Just make sure the PowerPoint is up and live. I guess you got two. Technology is grand, isn't it? There we go. All right. Does that was that look fine, Chris, before I start?
Yeah, looks great. We're up.
All right. So just a bit of background before I jump into this. I actually started my career working in British Columbia. So I'm no stranger to the Kamloops Exploration Group. I used to be a member. I've given short courses there back in the early 2000s, and used to present work that I did working up the North Thompson River Valley, Adams Plateau area, and as far down as Logan Lake, Merritt, working with Ray Lett and Peter Bobrowski, who were from the BC Survey at the time. So it's my pleasure to give a talk to KEG. So, because this is for a general audience, I'm just going to give a quick background. When I'm talking about dispersal trains, I'm talking about material dispersed by glaciers. And so why is that important? Well, most of Canada was glaciated. This is just a map of the Northern Hemisphere. Basically, the last main glacial event started about 120,000 years ago, roughly. There was cycles in between where the ice margins retreated a bit, but then there was a really big push towards what was called the last glacial maximum about 18,000 years ago. And then from then, things really shifted gears and the ice sheets retreated quite quickly. But that wasn't the last ice sheet. There was even early ones. And those sheets would have impacted the landscape prior to the last glacial event. And those earliest ice sheets actually would have scoured a very different landscape than what we see now. They would have scoured what we say is a sedimentologically mature landscape, or a landscape with V-shaped valleys and dendritic drainage systems and basically the type of terrain that you see in the middle U.S. today that was beyond the limits of the last ice sheet. And so why is this important for mineral exploration? Well, this is a map I rarely show at a conference because it gets so washed out, but with technology, it should show up just fine here. This is a mineral deposits map of Canada. And you can kind of see in a nutshell here, the majority of these mineral deposits are either A, in this big pink blob, which is the Canadian Shield, or they're in the Cordillera, which is home to the Kamloops Exploration Group. So as you can see, pretty much everywhere with mineralization in Canada was once covered by ice. And so early in my career, I decided to get into this thing because dispersal trains, I thought, well, Canada has been flown and lots of people have prospected. I figured deposits that occur at the surface were probably mostly already found, and new deposits were going to come buried under glacial cover. And that involved two career paths, one being geophysics and lots of math, and the other one being, understanding the quaternary geology and understanding the sediment cover. So I obviously chose the latter. Ironically, a bit of a, Phil's talk last week gave a little segue into what most people in my field of research here, and that is, if somebody asked Phil the question about, Pleistocene fossils, and he basically said, well, the Pleistocene is material we scrape away so we can see the bedrock. And I heard a lot of exploration geologists speak pretty much the same of the quaternary. But knowledge of the quaternary is powerful, and you can do lots with it to, I'd say, increase exploration success. So for those not familiar with the dispersal train, this is definitely not one. This is the train that runs from the Kidd Creek mine to the smelter north of Timmins. So just a little bit of humor here, but the whole concept of studying this was basically out of Western University by a gentleman, Alexis Dreimanis. And so he basically kickstarted this kind of research in Canada back in 1958. And his students really brought this type of research to the Geological Survey of Canada and to geological surveys across Canada. And here's Alexis here with his tie on and some of his students. And if you look real closely, this gentleman here with also wearing a tie underneath the lab coat is Ron DeLabio from formerly from the Geological Survey of Canada. And Ron's research really was what brought this to life and started to show how this information could be applied for exploration in areas with sediment cover where you couldn't see the outcrop. And this is some of work from Ron's thesis. And this is what a dispersal train is. You have this source material that's now buried under glacial cover, but it was eroded and transported down ice, and this train of material was formed from it. And so that's kind of a segue how I got into this as a career. So here's a very young photo of me. And my very first job with the Geological Survey as a summer student was working for Ron DeLabio and his colleague, Beth McClenaghan. So there's I am with Ron at Cape Breton, cutting my teeth on all good things glacial. Ron's work basically led into this model, which has pretty much been shown at every conference and short course through the 1980s and 1990s that I can remember going to. And it's just kind of three different views of how a dispersal train should be. There's a plan view at the top, cross sections, and a longitudinal cross section at the bottom. And so you sort of get the idea of what these things are. At surface, they have a very large footprint relative to the size of the original source. And so that's what makes them easier to explore for, to get your foot into an area for exploration. And of course, what you see at the surface, how it behaves and goes back ice is what's the research part that we're working on. So by the late 1980s, till geochemistry or looking at gold grains until really started to evolve in Canada. And so that what you're looking at is a numbered map of different deposits that were, or I wouldn't say deposits, but at least mineral occurrences that were found by drift prospecting and using sampling the glacial sediments. Just a little bit of a cartoon here to show how this happens. And so you have to envision ice as a bulldozer. And so the ice is flowing from the left side of the screen to the right side of the screen. And it's eroding at its base, but also while it's eroding its base, it's creating sediment. So it erodes and then uptakes sediment. So say if bedrock A is a mineral source, suddenly it erodes, but then it also lays down the sediment layer, which then the ice bed is moving on top of, and then it's taking a bit of that sediment later, and so on and so on and so on and so on. So it's a time transgressive process. So eventually your source material is buried, but there's a train leading from it, which is detectable at surface. And this is some of the research that we've been trying to understand as well. How does this time transgressive process work? And how can that help us then plug it back and understand dispersal trains? So I'm not going to go into the nuts and bolts of this model, but this is a time transgressive model of what we call a deformation front moving through time as the ice sheet matures or flows across an area till we have the present day ground surface. And this is what a model of that would look like. So this is the numbers you see here represent concentration. So 100% concentration would be your mineralization from an ore body. This is the concentrations you may see from that at surface. And so you can kind of see as the till layers are laid down and then material is continuously recycled, and you get the sense how material is first dragged down ice, but also up through the sediment column at an angle as well. And that is how models like this come to be, where you have idolized dispersal train models and what's exposed at surface versus what's at depth. And what's most interesting here is there's a lot of record of exploration companies where they map this at surface and then they lose it. And so naturally, where do they drill? Well, we'll drill at the head. Well, they would miss it because they don't understand that this whole thing has to climb through, especially in thick drift, thick glacial sediment. Sort of has to climb through the sediment package before you see it at surface. And here's sort of a visual example. So you see on the right-hand side here is an exposure. This is bedrock here where the solid line is. And this is glacial sediment. And you'll notice it's 3 different colors. It's 3 different colors because the ice sheet behaved differently through time here. But somewhere within that section, is material with mineralization in it. And so this is just a lump of till with a big chunk of galena in it. Galena is the primary ore for lead. I don't have very many text slides, so I promise I'll keep them super short. But using the geochemistry of the till, so analyzing the fine fraction or analyzing the industry used -80 mesh, it's been popular since the 60s and it's still used today. And sometimes, you hear the term soil sampling kind of used synonymously with it, even though it's something a little different. Indicator minerals are a different animal. So aside from gold grains, it really didn't gain traction and use in Canada until about the 1990s. And that's when the diamond rush started happening in the north. And the main difference is the size of the dispersal trains you get using indicator minerals. Because they're more robust, the indicator minerals are sometimes actually pieces of the ore itself. So then you can actually test that for, say, well, is this a good deposit? Is it fertility, for example, with diamonds? And they tend to be in the sand size fraction, so they're less impacted by and more resistant to weathering. So I'll show you one thing. So before, and this is, even though Alexis Dreimanis started with boulders and then he worked into chemistry in the 1950s, but the oldest record I could find of using indicator minerals until in Canada was from Nova Scotia, back in 1911, where they were digging shafts down to bedrock, trying to find gold veins, but they decided to pan the material as they were digging, and they picked up this dispersal train, And so they knew from striated bedrock which way the ice had flowed. And so they actually went back up ice until they actually trenched down and cross-cut the vein, the source of this. So this is truly sort of the start in Canada. But as I said, it was the diamond rush that really made this thing take off. And this is a map of samples from the slave Craton. And this is almost, this image is almost 20 years old now, but from the early 1990s till the mid 2000s, the slave Craton was basically peppered by industry for till samples. And these are not colored by, of course, mineralogy, they're just colored by concentration. So Icadi is in here, Lac de Gras. And what's interesting, even at this scale, this is a Craton scale map, you can see patterns come from these industry samples, even individual trains from specific pipes, for example, Kennedy Lake. And of course, you have a whole number of kimberlites in this area, but this is really where the use of indicator minerals was entrenched by industry. And this is just an example, the lower right is obviously what they're looking for is diamonds. And these are some of the indicator minerals that are associated with the rock kimberlite that hosts diamonds. So beautiful pyropes, chrome diopside, orange eclogitic garnets, and so on. These are olivines. And then sometimes you can get really lucky and find some beautiful grains here. So I have to give credit to Michael Bainbridge from who also does photography for Museum of Nature. I mean, he's perfected this to an art to photograph our indicator minerals so they actually look like tiny little works of art. It's just beautiful. And I was there in the middle of that in 1993. So that's me on the left, sporting almost a COVID style haircut. I actually miss having hair like that now. And that's Linda Dredge with the shovel. Brent Ward is sitting there on the, at the time he was a postdoc with the GSC and holding his favorite pick before I actually bent it about 90 degrees. And then and this young fella here is, some of you may recognize, that's Murray Gingras, now at the University of Alberta. He started his career in quaternary, but I think trace fossils won him over. So here's a quick example. This is from a dispersal of a major VMS deposit in Nunavut. And so this is what's called the Izok Lake deposit. It's a major deposit for base metals. If this deposit was sitting anywhere within southern Canada where you could build a road to it, it would already be a mine. So it's quite large. And the whole point of this is to show, here's a 2-kilometer scale bar at the bottom, is within 2 kilometers, you kind of lose the signal from this large deposit by looking at the geochemistry of the till. But when you look at the indicator minerals, you see a huge fan. And so this is a fan of an indicator mineral related to the zinc in this deposit. It's a zinc spinel. And you could just see that, here's a 1 kilometer scale bar, just how far we see this. And actually, what we're seeing here is the product of multi-phase flows. And I'll get into that a little bit later. But even at a reconnaissance scale, those original samples collected in 1993, where I showed you that picture with all my lovely hair, we took some of those samples and had them repicked for that zinc spinel. And we actually able to pick up indications of a major deposit. That's a 10-kilometer scale bar. So you can see how powerful indicator minerals can be relative to the till geochemistry. And as I said, these are little pieces of ore physically. So this is an example of sphalerite from northwest Alberta. And we were able to actually probe these little grains and show that they were not from a major lead zinc deposit 200 kilometers away. They were from a source that hadn't been found yet. So that was sort of the power of what we can do with indicator minerals. And that work in Alberta was done in 2003 with this very dapper looking gentleman right here. That is Alain Plouffe. So at the time I was with the Alberta Geological Survey and Alain was at the GSC. We already knew each other and we teamed up on a research project. And we basically, through our work, proved that there's mineral prospectivity in northwest Alberta for zinc. So how do you map these dispersal trains and what's important to know? Well, the biggest thing is ice flow history. So I'm not going to walk you through, that's a whole separate lecture in itself, to walk you through glacial landforms and how to map them and stuff. So I'm just showing this picture. You know, the striation record is very important to us in areas where the bedrock is competent enough to record the glacial movement. And this is the scratches you see from glacial polish on the rock. And I showed you an earlier picture with multiple colors of till. Well, multiple colors of glacial sediment or till is because the ice is sourcing it from that material from a different direction. And then what you're seeing here is the erosional footprint of the multiple directions. So, and this is a photo I took with Beth McClennigan, who I did my master's with in Northern Ontario. And there we are in 1993 at the beginning of my master's. We were measuring striae here on this beautiful outcrop in an area called Smooth Rock Falls. So again, the early 90s was great for hair production. And then when you see all these things on a map, what do you make of it? Because a lot of times industry gets a map for the area and they don't know really to make heads or tails of what they see. And this is a really good example from a map we recently published where these lines with the little circles in the middle are basically streamlined glacial landforms. And as you can see, you see at least 3 directions here where they're going. And what does that mean? And how do you interpret this in terms of glacial sediment dispersal? And so I'll try to show some examples of that. So we have to be really careful with how we interpret the landscape, especially with remote sensing imagery, that you may only see the last evidence of glacial flow, but that one might not have been the one that's dispersed and built your dispersal train. So this is actually took this photo out of an airplane flying up to Yellowknife, and I'm just close to Pine Point here, which is a former mine on the south shore of Great Slave Lake. And these large landforms are the dashed arrows, and the smaller ones are these little symbols with the arrow and the circle. And you can see those are just modifications of this material. So the material that's in these landforms is not coming from this direction. It's actually reworking material that's come from 90 degrees in that direction. There's another visual of the same concept. So this is in the Smallwood Reservoir of Labrador. You have an area here of outcrop. You had a tail of sediment produced from this older flow. A younger flow cross-cut this thing and robbed or cannibalized the sediment and produced a landform this direction. So even if a sample was collected here and it was full of indicator minerals, if you go chasing off in this direction, you may not find the source because this is actually reworked material from a source that came in this direction. So these are kind of like, I call it, it's a complex detective game. And you have to be really careful because sometimes you get really strong overprinting. So here you could see multiple directions of landforms. There's the little ones here at sort of the upper right, but you're seeing a strong influence in one direction. And that's what overprinting is the landscape is completely overprinted. Here's an air photo showing the older flows, the green arrow that came across this area. This is just south and east of Great Bear Lake in the Northwest Territories. And then the younger flow is this yellow arrow. And you can see how it's completely obliterated these landforms. And so overprinting is playing a major role here in spreading this material out. And so I'm kind of setting the stage here because I'm going to show you some really cool examples of real dispersal trains and how multiple ice flows impacted these. Because ultimately it's about how industry and how exploration people interpret these. And so I'm very cognizant of the fact that I'm speaking to a group where the term exploration is in its title. So here we see strong overprinted terrain. You're looking at Landsat images at both of these areas in the west side of Great Slave Lake on the right and the Mackenzie Valley on the left. However, when we look at the sediment and how the pebbles are aligned in that sediment, we know that older ice flows played a role in bringing that sediment there. And that this direction on top was just merely a late modification. And so that type of work and understanding is what Ralph Stay from Nova Scotia really got into, looking at multi-phase dispersal, how to interpret these forms, and what industry should expect to see. So in a very simple world where you have one ice flow, you have your source and you have a ribbon down ice in one direction. But reality is, we know most of Canada was complex glacial flow. So your sources here, you could have an early flow, which has produced this, and then this upper one has then been reworked by this other one. And if this outcrop is a positive relief feature where the glacier is eroding it actively, it's going to produce a second ribbon here, but then it's going to take this first material and also produce these other ribbons in the same direction. So you could see if you're chasing these things in the direction up ice of the last ice flow, you'll completely miss the target. And here's more sort of a newer model that Beth McClellan and I have worked on to sort of demonstrate this. So if the till is thin, generally industry won't miss it. You know, they'll figure it out pretty quick if the drift is, say, less than 3 meters thick in some areas. So perfect example is the diamond deposit or the kimberlites that occur in the Odish Mountains of Quebec. They basically were sampling it all over the place, and then they basically sampled literally almost on top of this thing and found it. But when the glacial sediment gets thick, it's a whole different ball game and animal to play with. So you can see the resulting footprint here. So what you're seeing is two versions. You're seeing a single ice flow direction, then you're seeing that modified by a later flow. And you can sort of see that not only is the surface footprint more dilute and larger, but its orientation is not going to lead you back to the source. It's actually the net result of these two directions. And you have to be really careful because sometimes the shapes of dispersal trains are from multiple ice flows, but sometimes they're not. And so there's very few examples in the literature, but this is one of the better ones. This is originally from Pam Strand's paper on the Rankin kimberlites. And so she had an area with basically what I would say was an ideal environment for exploration because there was basically a strong unidirectional ice flow in the area. And they were looking for kimberlites. This is when Pam was with shear minerals. And they found tons and tons of pyropes all over the area. But when they flew geophysics and drilled their kimberlites didn't have pyropes, but they were loaded with ilmenite. And so they had these ribbons of ilmenite, what you would expect to see with one ice flow direction, but then they had these fans of pyropes. And so it wasn't for a couple of years later that they discovered kimberlite dikes running almost transverse to ice flow. And these kimberlite dikes produce these large fans. Whereas in most cases, when you see a large fan, like the one I showed in Nunavut with that large VMS deposit, that fan is a result of multiple ice flow directions. But this fan is just solely a function of the source shape and size. So that's something that you know we have to keep in mind. Again, some more beautiful images. This is what a pyrope is. It's a beautiful chrome-rich garnet related to kimberlite, which hosts diamonds. So without explaining what this, you're looking at a thin section of till, and I'm not going to explain that because everyone's eyes will gloss over it. But I want to show the concept of inheritance of overprinting, and what that really means, and how you boil that down into layman's term. And the easiest way to do that is just show examples. So this is a former student of mine from Alberta who's now at the Manitoba Survey. Her name is Michelle Gauthier now, but she did this in her thesis, and I'm not going to walk you through this because it's kind of a complex thing, but look at the main titles where you have relict and complete preservation of glacial landforms. Then you have high inheritance, you're slowly mixing, complete reworking, and then if you have a high sediment supply, you just get layered stratigraphy. So this is kind of a, well, that was my mouse did that. This is kind of a continuum where you have like absolutely no reworking from later ice flow to complete reworking based on how much it's eroding and what the ice is doing. So that's about as much as I want to explain with that, but I will show you our excellent examples of each one. So no overprinting and a high inheritance. So this is a dispersal train from a kimberlite in an area at Cruntoido Lake. So the kimberlite is the red star, what you see here. And what you're looking at here are these little features that you see with sort of the U shape and the stick running through it. That's basically this glacial flow indicators. So there was two ice flows that impacted this area, an older one that went this way, and then a younger one that went almost north. And what this shows is you have a dispersal train in both directions. And what's really interesting is this dispersal train to the west here was not overprinted by ice flowing north that actually still eroded the source and carried this material. And again, this was for kimberlites and some beautiful kimberlite indicator minerals. So you have a really interesting boomerang here. And to put this in sort of a real life context, the company at the time spent a lot of money chasing these anomalies in this direction to the south, as opposed to recognizing the older ice flow. Here's another example from Saskatchewan, one that I worked on. So if you look quite closely, you'll see two orientations of landforms here. You'll see the black ones that are older, and or the ones I've labeled black with these symbols with the circle on them, and then you see the younger ones in white. And so there is one source to this uranium deposit, and these trains were outlined by boulders. So back in the day, they used to run all through the woods with a gamma ray instrument and track all the boulders, and they ended up with these two parallel trains, and they couldn't figure it out. Well, what happens is the original train was formed from this older flow, the ones in black, and then the younger one took that material from the original source as well as from the older source and reworked it into twin trains. And so this is just a little photo of uraninite that was actually found in the till. So again, pretty high inheritance there with and just a little bit of overprinting. We're back at Izok Lake, back at this VMS deposit, and I've color coded this fan now so you can see, and I use primary color. So blue is the oldest flow, yellow is the youngest flow, and anybody who's ever played with crayons knows that blue plus yellow equals green. And so the green fan here is inherited from the older flow. And the grains you see at the bottom, a zinc spinel is a very hard grain. Spinel is almost as hard as corundum. It doesn't abrade and round very easily. But what we are able to map actually is the adhering minerals get removed with transport distance. So all the quartz and the mica and the kind of the milky colored stuff you see on the grains is close to source. Down ice, you only see the grain and all the other minerals are gone. So this is a beautiful fan with a nice mix of overprinting and inheritance from the older flow. High overprinting, so more reworking and very little inheritance from the older flow. So I decided to take this example that should be near and dear to at least some of the people at the Kamloops Exploration Group. What you're looking at here is a dispersal train south of Merritt, a place close to called Iron Mountain. And so your regional ice flow, your main older ice flow is the large yellow arrow. And then this is in the Cordilleras. The ice sheets thinned, topography controlled ice then took over and reshaped almost all this original dispersal train. So you can see the orientations of these things are pretty much lining up now with the younger flow. So this is what's called high overprinting. And that was done prior to the year 2001. So I worked with Peter Bobrowski. There's me. And this was another younger student. This is Adrian Hicken. So you may know him now. He's now the head of the BC Survey in British Columbia. So Adrian was a student working with myself and Peter back in the day. That just shows you how small our world is. And you know, my advice to young geologists out there is never burn a bridge, because you never know when a student you work with might become your boss. High overprinting and minor inheritance plus layer stratigraphy. So you can kind of see, I'm not going to really walk you through this. It just, the thicker the till gets, the more complicated it gets. And the main thing here is the ore zone subcropped here. This is a former open pit for lead and zinc mine. And the main ice flows you can see with this black arrow going to the northwest, and this older one going to the southwest, created this sort of this amoeboid dispersal train. The last flow was this feature here, and that was the same, if you recall, the same photo I showed you when I looked out the airplane window and took the picture. This last flow had no impact at all on this dispersal train. And so again, and this is the site I showed you earlier with the sort of the Neapolitan colored glacial sediment. And this is the model we came up with. This last flow here, number 3, really didn't impact this dispersal train very much. And what that train consisted of for us was mostly sphalerite in a couple different forms, galena and anglesite, which is galena with a carbonate oxide coating. And that was in 2011. So that's when I worked with Beth McClenaghan, and I teamed up with John Menzies to look at and that's basically, that's how we built our deformation front model of how this till forming features happening over time. And then the next generation of students, this is Natasha Oviet, who now is one of the lead quaternary people for De Beers in Canada. And my new young protege, Jesse Rice, when he first started working with me, and now he's a postdoc at the GSC. So small world, and the cycle continues. A last slide showing complete reworking. So complete reworking is obliterates everything else, and you're left with a single ribbon from the last ice flow event. And this is an example from Ranch Lake that basically shows that. And it's quite interesting here, the concentrations of grains are higher the further away you get from source as opposed to the closer. And one of the explanation is that I think is reasonable is, prior to glacial times, kimberlites would have a very soft cap to them. They're ultramafic rock, and they're quite prone to weathering. But as the glacier eroded that weathered cap, and fresh kimberlite's actually quite hard. So once the glacier is hitting this hard substrate, its ability to erode it lessens. And so you have to remember this ice sheet is like a bulldozer or a conveyor belt moving across the landscape. And so as it's doing that, it's also incorporating rock around it, and it begins to dilute as well. So, and finally, when you have layered stratigraphy and very high sediment availability. So this is from the Western Canada Sedimentary Basin. If anybody's ever worked in Alberta, the tills there are very thick and very soft and full of basically the what we call soft rock, or the Cretaceous bedrock. And so here we had 2 ice flows that kind of crossed this kimberlite field here, one to the southwest, one to the southeast. The southwest one left this lower till, and you could see here just the number, more than 750 indicator minerals for kimberlite. The upper till, of course, didn't cross the kimberlite field and was just slightly reworking this. It didn't have to erode this lower sediment because availability was so high, and you can see here how little it has at surface. So now I'm going to sort of quickly show how this fits into a landscape system. So our original models for glaciation in Canada basically fit on this system where we had a cold-based center around the heart of the ice sheet, or the dispersal center, and then towards its margins, it was what's called warm-based. You have lots of water, lots of erosion, lots of sediment accumulation, and so on. And just a quick look, this is what cold-based terrain would look like with very little glacial erosion, because it's frozen to the bed. Here's the dispersal terrain in cold-based terrain of this dike rock. You can kind of see the colors of it. So material will just freeze to the ice and move down ice with no slipping with water. And when the Glacial Map of Canada came out in the late 1960s, this model basically fit the map. So it worked. And there was a whole bunch of stuff associated with that. How drumlins were formed, how landforms formed. There was this whole drumlin continuum based mostly on sediment supply and the maturity of the glacial sediment as you go towards the ice margin. And then this was since revised where we have this frozen bed still. And then we have this mosaic of thawed versus frozen, and we have ice streams. And this frozen bed still created this preservation of older landforms. And I've shown you some of this in pictures. I'm not going to walk you through that. But now we know that most of these major ice dispersal centers are actually what we call polythermal, is they were never cold based through the whole time period, or at least in most areas. There are some areas that were, that I showed you the one photo, for example. But elsewhere, say, especially in Quebec, Labrador, you know, you have the major ice dispersal center. That whole area was mostly warm based, and the cold based center was non-erosive. That just basically moved as the ice dynamics shifted. So this area here, and when it moves, you just get preservation from older flows. And so you can have dispersion in one direction, you can have a nice divide move, no dispersion, and then a complete, and as it continues to move, then it goes in the other direction. So you go to an outcrop like this, you see an ice flow going one way, then you see it going another way. Fun stuff, right? Lastly, ice streams. And the reason I want to focus on ice streams is because they're a real game changer, sort of a paradigm shift of how we understand deglaciation of Canada. And ice streams are like literally rivers of fast flowing ice relative to the ice around it. So this is just an image of Antarctica showing the colors here represent ice velocity. And you can kind of see the hot colors here represent corridors of fast flowing ice. And I'm gonna paint a quick analogy here. This is a really good friend of mine. This is Nick Isles, who I've been recently publishing papers with. And Nick's an avid motorcyclist as well as me. So Nick rides this BMW and he goes everywhere with it. And I like to refer to his bike as steady state glacial flow. So an ice stream would be my bike. Nick always gets really mad when I show this because I can almost hear him chortling now. So this is a map that was produced in 2015 showing some of the major ice streams in Canada. A lot of the soft bedded ones in the Western Plains, but also some of the hard bedded ones on the Canadian Shield. And this fast flowing ice really impacted the landscape. And the smoking gun for what we know as fast flowing ice are these mega scale glacial lineations from on these bed forms. So, you know, you can use form analogy, but at a 1-to-1 scale. This is from an active ice stream or recently active ice stream in Antarctica, and this is Dubont Lake, and you can see the scale bars the same size. And so this is an example from northern Alberta. Here's another example from northern Alberta. This is actually an upland area, the Cameron Hills, showing a beautiful ice stream, and just the type of features formed by fast flowing ice. So what does that do? Well, these streams can start and stop for any reason at all, and as ice dynamics shift, they can shift. So here we see a large ice stream, an older one that was truncated by a younger ice stream. That creates a mosaic, a landscape mosaic of different materials. So what you're seeing here is the large bubbles represent the amount of Paleozoic carbonate rocks or content you find in the tills at the surface. So this isn't a time transgressive process in terms of layer cake material by glaciers. This is all at the surface. So depending where you sink your shovel, you're going to have material that's not affected by ice streams in these areas with high carbonate from ice flowing off the shield this way versus stuff that cross-cut it afterwards that is low in carbonate. So you have two different tills at the surface. So it's a bit of a different concept. And our old drumlin continuum based on what we thought was, you know, proximity to ice margins, sediment supply, and maturity is actually, some of it's actually related to what's happening at the ice margin is controlling or retrograding back into the ice sheet, and velocity is a big thing that controls this transition from the drumlins to these fine forms. So this is a paper we just submitted a week ago. And what do dispersal trains look like with ice streams? Well, this is from the same paper we submitted a week ago. This is a specific type of bedrock, a sandstone bedrock, and then this is the concentrations in the till, and you can kind of see these fingers of elevated concentrations in the Finger Lake areas, how aptly named. And so these ice streams are actually taking this stuff a lot farther. Here's a quick example from the Melville Peninsula where there's no trees, and this makes it really easy. So the white here is not snow. This is glacial sediment derived from Paleozoic limestone. And then you see these wisps on the landscape. These wisps are actually ice streams that took off during deglaciation and took this material and dragged it out over the Canadian Shield. And that's what actually, here's one that actually looks like from the air. If you follow my mouse here, it's curved. And we are at least 120 kilometers away from the bedrock source that has this Paleozoic limestone. If you were to sink your shovel here, you would find zero class content of any limestone. You sink your shovel here and it's about 90%. So that just tells you what ice streams can do for mineral dispersion and what it can do to really have people scratch their heads in terms of transport distance. So a lot of the dispersal trains I showed you were maybe at most 10 to 15 kilometers long, but you get in an ice stream, it's a whole different animal. So here's an ice stream that went over the Aviat Kimberlite field, and here's a scale bar down here. This thing is about 80 kilometers long for a dispersal train from a small kimberlite field. Here's Strange Lake in Labrador. Strange Lake is a rare earth deposit. And for the longest time, this was considered to be a product of long-term or long-time unidirectional glacial flow. So the ice flow didn't flow any other directions, but through time just eroded and eroded and created this beautiful ribbon. And just to show off some pretty minerals that I will not try to pronounce for you, but you know, this deposit has some very cool and funky minerals as indicator minerals that you can track down ice from it. But when you look at it on this is the same, whoops, my mouse does that. This is the same source, the same outline for Strange Lake, but on the shuttle radar data. And you can just see this thing is smacking the trunk of an ice stream that took off to the coast. And this is the airborne radiometrics that show this beautiful ice stream. And what was originally done in the 80s when this was discovered was it stopped here because these little circles is where the till samples stop. But you can see by the airborne spectrometry, this thing keeps going. And in fact, if you look at this recent compilation of lake sediment data, Strange Lake sits right here on the border. And regional structural geology, this is the core zone here, and you have you know, the Nain block and big cratonic sweeps through here. The main structural geology follows or parallels the coast. And then you have this weird geochemical ribbon going all the way from Strange Lake right out to the coast. And that's what you're looking at is tin. Well, tin is affiliated with para-alkaline granite intrusives, which is the host rock for this rare earth. So that just gives you, you know, that's a 200-kilometer scale bar. That just can show you how far ice streams can drag this stuff. And what we're seeing is, you know, why do you see this? And that's for a whole other technical talk and source, but we don't see the type of decay. If you remember that very early dispersal train I showed you by Ron DeLabio, where it had a peak very close to the source and it tapered off quite quickly. In ice streams, these things tend to be way more linear. So that's all I'm going to talk about that. For those that are exploration minded, there's lots of references out there. The most recent one is a chapter that Beth and I wrote in this book. It's not open source, but if you email me, we'll send you the chapter basically. I also recently put out a video with NRCan that's kind of aimed at the general public to show what it is we do, how we do this in the field, how we sample, and so on. And so it's quite good to show to people who are not familiar with prospecting even in general. And this is my last slide, so I will stop sharing my screen and open the floor. So it's kind of a whirlwind 45 minutes there.
That was, thanks, Roger. That was fantastic. It took me around. I did work in Newfoundland too, so it took me right back to Labrador. We have a couple things have started to come in. So first of all, Michael just wanted to say hi and thanks for the invite. So,
That's probably the Michael, the gentleman who took those beautiful photos. So if I don't know if you saw the scale bar of those photos, but those are literally grains of sand, about 1 millimeter in size. And so anybody who's ever tried to do micro photography, you try, and basically it's from image stacking. It's just like, blows my mind how it is an art to somebody to photograph a grain of sand to that clarity and focus for full depth of resolution.
they were so clear. It was amazing. Yeah, so we have about 10 minutes, and okay, we have a questions just come in. So, do you imagine a day where geochemical analyses of till is delayed or avoided in favor of indicator analysis?
That really depends what you're looking for. And it's a cost thing too. So you have to weigh the balance of a geochemical analysis. If you run like the full suite, major oxides and so on, that might run you $75. Whereas an indicator mineral sample with the full suite of minerals, if you want to look for everything, will run you north of $450 a sample. So it depends where you are in the country and what you're looking for. So if you're looking for diamonds, you need indicator minerals. If you're in the Cordillera and you're looking for polymetallic or even precious mineral deposits, till geochemistry has worked. You just need more samples and tighter spacing. So I don't know if that really answers this question. I don't think there's going to be a day. I mean, they both work well together. So I would argue if you're in a brand new area, using indicator minerals, but with stream sediments is probably your best shot at getting a sniff. Oh, is there something here? And then when you really want to hone in on an area, you can pepper a 10 kilometer by 10 kilometer block with geochemistry.
Yeah, it's a great tool to put in your toolbox for sure.
Yeah.
Catherine Hickson says, I love the ice streams. How do they manifest in the Cordilleran steep terrain? Are they more topographically controlled?
Oh, absolutely. So there's lots of things that can control an ice stream. The ones in Antarctica, some of them are even controlled by geothermal melting at the base of the ice sheet. So it's all about reducing the friction and increasing the pore water pressure at the base of the ice sheet and allowing it to flow fast. And sometimes the margin controls that, but topography is a big player, and especially in the Cordillera. So there's a couple papers that's come out in I think 2018 on ice streams in the Cordillera, and there's lots of them.
Okay. Okay. Is it more difficult to do this work in BC? That kind of follows off Catherine's question.
I have worked in BC. When I worked in BC, I wasn't working with indicator minerals. This was the late 1990s to early 2000s. I would say no. The most difficult to do that would be the Western Plains, because you have thicker drift and you have no erosional record. The bedrock is so soft it doesn't preserve striae. So in the 7 years in Alberta, I only measured 2 striae. One was off a coal seam and the other one was literally off a kimberlite. And you're standing on the source, so it's kind of pointless to figure.
Well, good answer, I guess. Where are we at? Do ice streams exist in alpine environments, or does paleotopography trump them?
Oh, absolutely. I mean, a good example is when you hear about a glacier surging. So in Alaska, the surging glaciers are technically an ice stream, but generally, I deal with this at a continental scale. So for sure, I mean, the north part of Washington State, has a very famous drumlin field that was probably a product of a large ice stream. But when you're talking about alpine glaciers locally, I probably not, you know, like because technically an ice stream is a fast flowing corridor of ice contained by slower ice. And generally when you get a surging glacier, the whole thing is something is happening, whether it's calving at the margin or something, right? But um, topography does play a big role.
Great. It is so great to see this work in which the quaternary mapping is relevant for prospecting. It seems like ice flows are actually quite critical to reconstruct. Your talk convinced me that the flows do not necessarily follow glacial retreat paths. Is that right?
Well, you have to be careful with the words there. So the last flows do, but the sediment that was placed there might be the product of older flows from different directions. So the example I gave from Pine Point is really good because the last ice flow was from an ice stream. So it created those very fine forms all across the region. But all that really did was cannibalize previously deposited material and scrape it. So if you think, you know, a good example is you think of a carrot cake with a nice thick cream cheese icing, you know, and you spread that icing in one direction, and then if you took a fork and dragged it across a different direction, well, what you're gonna see at the surface is very different, but what you normally underneath is from when you first put it on, right? So it's not just, and that's not true everywhere. So you're right, like you have to also look at different ice flow directions, but then you have to look at glacial vigor. So how strongly preserved are the older ice flow directions? So the area where I worked, Dyzoc Lake, and you know, the hardest rocks in the Slave typically are the Mackenzie diabase dikes. They're very, very hard rock. And so one thing we noticed was the beautiful sculpting of those diabase dikes were from the oldest ice flow. And then the younger ice flows just strided across them. So so that gave us a sense of like the older ice flow was stronger. But elsewhere, you know, when you get complete overprinting, like at Melville, you know, then obviously the last deglacial flow with streaming ice was the most important because it's taking this carbonate stuff more than 100 kilometers away from its source.
Fantastic. So Riley says, great talk, Raj. What's worse to work with in deciphering drift prospecting signal? Complex bedrock geology or complex ice dynamics / flow history?
That's a tough question because in the Cordillera, the complex bedrock geology would be the main factor. You know, we were mapping dispersal trains parallel to stratabound sediments. And so you have these long trains, but you also have multiple deposits along a specific stratigraphic horizon that was parallel to ice flow. So in the Cordillera, the bedrock geology can be a real animal. Whereas you get on the Canadian Shield, I'd say anywhere where you have a complex ice flow history and thick sediment. So obviously thick sediment is the big thing because you have to figure that out and unravel where the source of the materials from, what ice flow is, whether it was an erosional or a depositional system. It's probably the best way to answer that. No, there's no uniform formula for this. If there was, I wouldn't be working for government.
The answer is always in the middle, right? There's one extreme, the other extreme, and the answer is somewhere in the middle. We're going to jump to the last question that just came in because I think it's a cute one. Emily, 11 years old, would like to know how fast the ice flows move.
Well, when I say it's an ice stream, it's still relative. It's still at a glacial pace, but steady state flow might move tens of meters, or even like, yeah, tens of meters over a year if it's got lots of water at the base. An ice stream might move a couple hundred meters in a year. So it's relative. You could still outrun it, that's for sure.
I don't know. I'm not a very good runner. Where are we at? Oh, Bruce has said Dr. Hickson was asked to pronounce the E volcano in Iceland. So you get to pronounce the Icelandic J word for a glacial dam burst.
Well, and I know Bruce because he took over in Kamloops there when Mike Cathro left. So I believe the word he's looking for is yokalip.
Yokalip.
So you get lots of geothermal activity in Iceland, and so if you get enough of it under an ice sheet, it'll build up a large amount of meltwater into the ice, and then it'll reach a point where it just flushes out.
That's fantastic. Bruce has got lots of little tidbits. Do you think it's beneficial to attempt to model the quaternary geology in fine detail with 3D software to vector for mineralization?
If you have 3D data. I mean, that's what early days of overburden drilling was. You know, they used rotosonic drilling, or they used what's called reverse circulation drilling, mostly for gold grains. They would pepper an area and look at the three-dimensional layering and where they were getting the gold grains from the reverse circulation, and then eventually build a 3D model to go back. And so a really good example of that, and I can provide a reference to that because it was Rainy River. The Rainy River gold was like 30 years of reverse circulation drilling through the Ontario Geological Survey, but also with overburden drilling management. And Stu Averill wrote a paper on that sort of once all the data became public. So yeah, that's ideally you got to have the data to populate a 3D model.
Fantastic. Kathy says, love the last question. Good try, but you won't be mistaken for an Icelander. She says, nor will I.
No, it could be mistaken for a Cape Brettoner, but that's about it.
The map showing the ice streams across Canada showed that the ones in Alberta were pretty simple in comparison to the ice stream paths in Saskatchewan. What controls the pathways?
That is a good question, because there's a lot of new research on the ice streams in Alberta. Even as most recently as 2019, a major paper came out for Southern Alberta. I think proximity to the ice margin is one factor. And so these are a feature that, at least in the Western Plains, it's also a time transgressive thing. So as the ice margin is retreating, in Alberta, a lot of that was the ice margin was proglacial lakes were basically all against the edge of the ice margin, because in Alberta and at least in the western part of Saskatchewan, you know, your glacier is retreating, but the continental slope is going towards the ice. So all meteoric drainages are going towards the ice margin, and you have a lot of water. And surging into those glacial lakes was probably a simpler process. Whereas in Saskatchewan, I think at least some of it was not controlled by glacial lakes, but just controlled by what's happening in terms of where the ice is thickest and where it's thinnest and where it wants to go. And the bedrock geology. So anytime Cretaceous shale got involved, well, that's a good mechanism to reduce friction.
That's fantastic. So on that note, we have no more questions. And on behalf of the Kamloops Exploration Group, I would like to thank all of you, our attendees. Tonight we have had 72 attendees join us, and we'd like to thank you for all of your support. And we cannot thank Examin Mining Corporation enough for their sponsorship, and a huge thank you to you, Roger, for your time this evening. This truly was a killer talk. Our next talk will feature Dr. Rob Young on February 25th, and his talk is titled, "You Are What You Eat, or Are You? An Exploration of the Environments That Made Us Who We Are." As always, for more information about the KEG Virtual Talk Series, please go to the KEG website at www.keg.bc.ca. We'd love to hear your feedback. Please send it to the Countless Exploration Group at countlessexploration@gmail.com. And on that note, a huge thank you to Examin Mining Corporation. Roger, Paulen, of course, thank you very much. It was a wonderful talk. And thank you to all of you for attending. And we look forward to seeing you all on February 25th for You Are What You Eat, or Are You? An Exploration of the Environments That Made Us Who We Are. Have a great night, everyone.